Yeah, I think you can start, Linus, whenever you want.
So you want me to just start?
Yeah, I think whenever you can start now. I think it's fine.
Okay. So thank you to the organizers for inviting me to talk about my work. Uh, so I decided to talk about a paper that appeared last year. It's together with three students, Aviral Agarwal, Stephen Shia, and Ahmed Kamal, and a postdoc, Shubranil Chakrabarti. And it's about the Riemann to the 4 correction to supergravity in 10 and 11 dimensions, or string theory and M theory. So let me start with a few words of motivation. So we know that in the quantum theory of gravity, Einstein's theory is just the lowest order action, and we have higher derivative corrections, and these will typically be suppressed by powers of the Planck mass. So you could have something like the Riemann tensor squared suppressed by the Planck mass squared. And these corrections, typically they're very small because they're suppressed by high powers of the Planck mass, but in extreme situations near cosmological or black hole singularities, they start to become important. So there's some cases where we're very interested in what these corrections do. Now, in string theory, we know how we can compute these corrections. Although it can be very difficult, we know in principle exactly what we have to do to calculate all these corrections. In fact, in string theory, there are two kinds. These corrections come in two families, basically. And the low energy effective action of the massless fields of the closed string organizes itself into a double expansion. So the low energy effective action has the sum over two integers k and l. And we have this alpha prime to the k and gs, which is a string coupling, to this power, to l minus 1, okay, times the corresponding correction. Alpha prime is, as I'm sure you all know, the inverse string tension, and gs is the string coupling, as I said. So the first of these, the alpha prime corrections, are often referred to as stringy corrections. They come from the stringiness of the string as opposed to point particle theory, where they would not be there. The string has some finite size, and that's what gives rise to these corrections. In the point particle limit, they would disappear. And the second set of corrections, those that are parameterized by the string coupling, come from string loop corrections, so the genuine quantum corrections in the string theory. And the string coupling itself, there are no free parameters in string theory, and the string coupling is controlled by a field. It's controlled by the expectation value of the scalar dilaton. So GS is given as e to the expectation value of phi. Now, here I want to focus on the maximally supersymmetric string theories, which are called type 2 string theories. There are two of them, type 2a and type 2b. And the massless field content of these are the following. So both of them have a sector in common, which contains the metric, the B field, which is an antisymmetric two-form field or two-index field, and this scalar phi, the dilaton, which we already met, which sets the string coupling. So these three fields are common to type 2a and type 2b. And then type 2a and type 2b have some additional fields. So type 2a have Ramon-Ramon fields, which is a 1 form, C1, and a 3 form, C3. And type 2b has a 0 form, a 2 form, and a 4 form instead. So type 2a has two extra odd form fields, and type 2b has three extra even form fields. And then, of course, it's maximally supersymmetric, so there will be corresponding fermionic partners to these fields, which I will not say too much about here, but there will be two 16-component gravitinos and D Latinos of opposite chirality in the type 2A case and of the same chirality in the type 2B case. And that's basically the difference between type 2A and type 2B. Now, it turns out that in these two maximally supersymmetric theories, there are actually no corrections at order alpha prime and alpha prime squared, so which corresponds to k equals 1 and 2 in the sum. So those corrections vanish because of the very large amount of supersymmetry. And the first correction occurs at the third order in an alpha prime, so it's proportional to alpha prime cubed. And it was found originally by calculating the tree level 4 graviton amplitude in flat space. And doing that, this calculation was done in the 80s by Gross and Witten. And if you do that, you find a correction at order alpha prime cubed, which involves the fourth power of the Riemann tensor with some particular tensor structure, which is encoded by this T8, which we'll come back to, and an interesting coefficient in front, zeta of 3. Okay, so this is the Riemann zeta function. And then, of course, there are a bunch of other terms which they didn't compute. There will be terms involving all the other fields, so the B field, the Ramon field, and so on. So this is just a term that involves the metric. And then there will also be terms of higher order. In fact, it is known that there is another term which involves the Riemann tensor to the fourth power, which is usually written epsilon 8 r to the 4. But the leading term is a total derivative, so it starts contributing at the 5-point level. So I will not say much about it because I will be focusing on the 4-point level here. Another important fact is that at the 4-point level, the one loop amplitude actually has exactly the same structure as the tree level amplitude. So this you can see when you formulate the amplitude at tree level and at one loop, you find that they're proportional to the same kinematic factor. So they actually have the same structure at the 4-point level. This was also understood in the 80s. And the only thing that differs at the 4-point level is the coefficient in front. And you find that the one loop correction, so this corresponds to, in my expansion here, k being 3, which is alpha prime to the 3, and L is 1 now, is the one loop correction. It has a coefficient zeta of 2 instead, so pi square over 6, but otherwise the same structure. Although this the higher order terms and so on will differ. But the only thing at the 4-point level, the only thing that differs is the coefficient in front. In fact, it's believed that there are no higher perturbative corrections to this r to the 4 term due to a non-renormalization theorem. But there are non-perturbative corrections in the type 2b case, but there are not even non-perturbative corrections in the type 2a case. This has been argued famously by Green and Van Hoop in 97 paper.
Hi, Linus. Do you remember
Yes.
why there is no non-perturbative correction in type 2a? What was the argument?
I think basically there's no candidate for something that can give rise to a non-perturbative correction in that case. I think that's the only, and then also these arguments connecting 10 and 11 dimensions that we'll get into a little bit.
I see.
But there's no proof of that as far as I know. It's all this
In type
is at the
2b, it
level of
was
argument.
something like d instanton in type 2b that contribute to.
Yeah, exactly. It's known that you can have some non-perturbative corrections there. And then also this connection with the 11 dimensions gives rise to non-perturbative corrections.
But somehow, if you compactify to 9 dimensions, type 2b and 2a should give the same result.
Right.
So yeah.
Yeah, but what happens there?
Yeah, I think
Well,
in
you
2a
get
case, you
additional.
can have the membrane find on a two torus or something like that.
Right. I mean, there you get a bunch of additional
Yeah.
corrections, right? So that should resolve it. But I don't think anyone has analyzed this really in detail.
Okay.
What happens there?
Okay,
but thanks for the question. Okay, so it's believed that the strong coupling limit of type 2A theory is an 11-dimensional theory, which has become known as M theory. This is a famous paper by Witten in 95. And its low energy limit, the low energy limit of that 11-dimensional theory, which is supposed to be 11-dimensional supergravity, and it's not hard to see that it reduces to type 2A supergravity with a suitable dimensional reduction ansatz, which we'll come back to what it looks like. Now, since the one-loop correction to type 2A is independent of the dilaton, because at one loop, remember, you have this factor of gs to the 2 L minus 1. So if L is 1, there's no gs in this expansion. And so, so this is, the one-loop correction is actually independent of the dilaton. So that means it has a finite uplift to 11 dimensions. But this suggests that there should be a correction in M theory, which has a similar form, which is essentially the uplift of this correction. So I will put a hat on everything that's in 11 dimensions just to distinguish it from 10 dimensions. So L1 hat is the first correction in 11 dimensions. And the coefficient should be the same as the one-loop correction type 2A. And there should be some r to the 4, well, r hat now, because this is the 11-dimensional Riemann tensor. So a correction like that, you would expect to be present in the M theory effective action. You can also argue for this from anomalies and supersymmetry, but it's slightly more involved. So you would expect something like that in an M theory effective action. And what I want to do is to describe the form of these corrections at the four-point level, so the full correction at the quartic level in fields, and to verify that indeed the reduction of the 11-dimensional correction gives the correct terms in 10-dimensional type 2A, up to the overall coefficient, which you have to fix in some other way, because we have no direct way of calculating the M theory effective action. Yeah, and you should interrupt me at any point, by the way, and ask questions. Right, so the outline is something like this. First, I will discuss the type 2 r to the 4 correction at the 4-point level. And then we'll discuss the 11-dimensional correction, which it turns out you can compute from, well, you can find the structure by looking at superparticle amplitudes in 11 dimensions. Then I will discuss the relation between 11-dimensional supergravity and type 2A supergravity, which is well-known textbook story. And then I will show how we can compare this 11-dimensional correction that we calculated from superparticles to the type 2A r to the 4 correction. And finally, I will discuss how this leads to let us come up with a simpler expression for the terms in 11 dimensions than has appeared previously. Okay, so first we'll talk about the type 2 r to the 4 correction, the 4-point level. So to find this correction, we know what we should do. We should compute the 4-point closed string amplitude. And as we said, at the 4-point level, there's actually no difference between tree level and one loop, except in the overall coefficient. So therefore, it's enough to compute the tree level 4-point amplitude, as long as you're just interested in the 4-point level, which is good because that is a bit simpler. Well, in this case, it's actually the same, but okay. Now, the easiest way actually to compute this amplitude is to think of the closed string as 2 copies of an open string. So these are the famous KLT relations, essentially, which tells you that the closed string amplitude is essentially a product of 2 open string amplitudes. So you take 2 copies of the open string, and that gives you the left and right movers of the closed string, basically.
Hi. Here, you mean the amplitudes are the same, but terms beyond that to the form could be different. The completion of the index could be different, but amplitudes
Sorry,
are the same. And
sorry,
the 4-point amplitude are the same, but beyond the 4-point, they can be
yeah,
different.
beyond 4-point, it will be much more complicated.
Uh-huh.
But I will only talk about the 4-point level here.
The 4-point effective action are exactly the same.
But you mean the tree level and one loop are the same? Yes.
Yeah.
Yes, and beyond 4-point,
Okay.
they will differ. Yes.
Okay, I see. Okay.
Yeah. And right. But I'm just for this talk, I will confine myself to the 4-point level. So I will construct the correction at the quartic order in fields, and then there will be higher order terms. And finding those will be much more complicated, but we'll come back to that at the end. But to calculate the 4-point tree level closed string amplitude, I will use this trick, writing it as the product of two, basically a tensor product of two open string amplitudes. Okay, so then I reduce the problem to calculating the 4-point amplitude for the open string instead at tree level. So how do we do that? Well, first let's recall that the massless fields of the open string are a vector, AM, and a gauge genome, lambda. And their low energy effective action is precisely that of 10-dimensional maximally supersymmetric Yang-Mills theory. And the 4-point, if you calculate the 4-point amplitude, that will give you the first correction to this low energy super Yang-Mills action. And it gives you a correction that involves the fourth power of f. Okay, so you notice the similarity. The first correction in the type 2 string is the fourth power of the Riemann tensor. The first correction to the open string is the fourth power of the field strength of A. Okay, that's not a coincidence. In fact, this F4, this first F4 correction is precisely what you get if you expand the Born-Infeld action. So the Born-Infeld action involves the square root of the determinant of eta plus f. If you expand that out, you get the f squared kinetic term, and then you get an F4 term, and then you get higher order terms. That F4 term that you get, I mean, this is just schematic. Of course, it has some specific tensor structure, but that is precisely the F4 term that you get from the 4-point function. So now you can either compute this 4-point function directly, which people have, of course, done, or you can do it by saying that you want to have an F4 term and supersymmetrizing that, and you will find a unique answer. And that gives you the correction to the open string effective action, and it turns out to take the following form. So the first correction to the open string effective action coming from the 4-point function looks like this. You have a trace of f to the fourth. Okay, I'm looking only at the U1 part. If you look at of course, you have a non-abelian gauge field, but to simplify my life, I will look only at the U1 part. You can do it for the full non-abelian one. It looks more complicated, but since we are only interested in the quartic level, the difference will be in higher order, the fifth order and higher terms, and those are not interesting for us. So
Well,
it's enough to look at U1 part.
Hi, Linus.
Yeah.
Has the Yang trace f to the 4 being supersymmetrized?
Yeah, this is the supersymmetrization.
Yang-Mills, I see.
Yeah.
But somehow you
So
cannot write as a square root anymore? Or?
well, this is one. So as I said, this is the first term in this. It's the second term in this expansion, or third, depending on. I dropped there should be a 1 also, but okay. The first correction that comes from this expansion is the F4 term, right? And then there will be F6 and so on.
I remember in the past, people say there's a problem of writing a Born-Infeld type action for non-abelian gauge field.
Yes, that's true. So
some perturbative way you can write it.
I mean, you can compute it order by order, but there's no. So in the Born-Infeld action, you made the assumption that the field varies slowly. Basically, you're dropping derivatives on F. Because in the effective action, you normally have terms with derivatives on F2.
Yeah.
But in the Born-Infeld, approximation, you drop those terms, you say that the fields are varying slowly, and you find the Born-Hammond
Mhm.
action. That works when you have a U1 gauge field. But if you have a non-abelian gauge field, the commutator of two derivatives gives you F itself. So if you're saying the derivative is small, then you're saying that F is small, and then it becomes inconsistent. So there's no Born-Infield approximation in the non-abelian case.
Oh,
You can, of course, compute the full effective action, but it will have a bunch of terms with derivatives on F also.
it cannot be resummed as the square root of something. Okay.
I thought that
Well,
order
presumably
to the
part of
four
it will
is
contain some
computed.
square, but then you also have to decide the ordering of these Fs, right? They no longer commute with each other, and it becomes complicated. But I mean, at this level, since I'm just looking at the U1 part, I can ignore those subtleties. But it's true that if you want to write the full effective action in the non-abelian case, it's going to be something very complicated.
But if
But at the 4-point level, or the first correction, is just precisely this.
Yeah, I think Gabriel has some.
No,
Sorry?
I just try to remember at the f to the fourth level. I thought that the symmetrized trace prescription was working, or am I wrong?
Yes.
So I mean,
That's
in the non-abelian case, at least at that order is known. I
yes.
think.
So
I don't know about the supersymmetric extension.
right. So I wrote it only for the U1 part, but the full non-abelian one is known. But I don't need it here because I'm only interested in the 4-point function, and they will differ only in the abelian and non-abelian one will only differ in higher in terms of fifth order and so on. But it's true that it's known.
Does
And
the
it's
trace works in all order? Or?
no, it works only at the quartic order in F.
I see.
So the F to the sixth term is not a symmetrized trace.
I see.
But it's at least partially known. I think the F terms are known, but not the full supersymmetrization.
No, but I think that he is confusing the trace over there with, I mean, the trace written there, I think it's a trace in Lorentz indices, but then there is another trace that is the symmetrized one that I was talking about.
Yeah, there's a trace over the gauge indices.
Indices.
But yeah, that's part of the reason I only wanted to write the U1 part, because it becomes more cumbersome to write the
Oh, yes. Your trace only means, okay, the Lorentz part.
Yes. Yeah, because I'm just looking at the U1 part of the gauge field here. Okay. So then you get either by calculating the amplitude and just taking the U1 part, or supersymmetrizing F to the 4, you find this, right? So you find it's not just trace of F to the 4, it's this combination of trace F to the 4 and trace F squared squared. And then you have the terms involving the fermions to make it supersymmetric. Now, it turns out to be convenient. I mean, here it doesn't make much of a difference, but for the closed string case, it's convenient to introduce this 8-index tensor T8, and it's conventional to do this. So you define this 8-index tensor in the following way. If it's contracted with 4 2-index antisymmetric objects, M1, M2, M3, M4, right? I just write it as T8, M1, M2, M3, M4. It means this, and it's defined in the following way. It's 8 times the trace of the product of these things as matrices, and then minus twice a double trace. And then we take we sum cyclic permutations of 2, 3, and 4. And if you define this T8 tensor in this conventional way, then you can write this correction in a slightly more compact form. The first two terms combine to just T8 F to the 4. Well, it's actually 1 over 4 factorial T8 F to the 4. Okay, and the terms involving fermions are the same. Okay, so that's our answer for the open string 4-point amplitude. We focus on the U1 part, which is enough for what I want to do here. Now, what we want is the closed string amplitude. So we use the KLT relations. So we say that the closed string amplitude, or actually in this case, you can do it with the Lagrangian itself, the correction itself. So the closed string correction is just the product of two open string ones. And at the linearized level, when you take the product of these, you should interpret the product of f, of one of the f's with the other copy of the f. That becomes this curly r, which is the Riemann tensor minus the derivative of h. And this whole combination, this curly r, is the connection that you get if you take the spin connection to have a torsion given by the field strength of the B field. Okay, so you shift the spin connection by h, which you can do. That gives that means that you have a non-zero torsion, and the field strength of that gives you this curly r. Okay, and that's the combination that appears. Right, so that's from f times f, right, here. But we also have this lambda. If we have lambda tensor another lambda, we get some bosonic field, right? Because these are fermions. Two fermions make a boson. So what are those bosonic fields that we get? Well, from here we get the Riemann fields. In fact, this will give us, because they're two spinor indices, this gives us some bispinor. And I wrote it as F slash. It's the bispinor that contains the Riemann fields. So when you expand it out in gamma matrices, you find the Riemann fields of either type 2A or type 2B. So in type 2A, we have F0 if you include the Romann's mass. You have the field strength of the 1 form contracted with 2 gamma indices, and the field strength of the 3 form contracted with 4 gamma indices in this way. And a similar expression for type 2B. And then we, of course, have tensor products where you take F times lambda or lambda times F, and that will give you the two gravitino field strengths that you have in the closed string case. Okay, so that's how the closed string fields get constructed from tensor products of open string fields. So now we basically just take this action and we tensor it with another copy of it, and we use these rules. I would just focus on the bosonic fields. And if you do that, you find the complete R to the 4 quartic Lagrangian in the closed string case, and it takes the following form. So the first term should be clear where it's coming from. You have 1 over 4 factorial T8 R to the 4. So that is coming by taking the tensor product of this guy with another copy of the same thing. So you get 2 T8s, and then F times F gives you this curly R. So that gives you this torsion-fold Riemann tensor to the 4th power. And then these other ones are coming from combinations of fermions and Fs. Okay, so the tensor product of two of the fermions gives you the Riemann bispinor F slash. So I've colored the NS and S sector fields in blue and the Riemann sector fields in pink here, so you can distinguish the terms basically. So you get an R to the 4 term, an R square F square term, where F are the Riemann fields, and then you get F to the 4 terms, the last 3. And then, of course, we have the fermionic terms, which you can also easily get, but I will not write them down here. So this expression actually coincides with the expression that was written down by Polycastro and Simpis, who did this, and they also computed the amplitude directly for the closed string and verified. So they used the pure spinor approach to compute it directly, and they verified that it's the same. They did this in 2006. But I fixed a small error in the R square F square terms, and then I've simplified the result a little bit. Okay, so it takes a relatively compact form when written like this. I should say that this T also just means the transpose of these expressions. So if you transpose the gamma matrices, these combinations of gamma matrices are just symmetric or anti-symmetric, so you get some extra signs if you take the transpose.
But in the effective action, the F4 action for the U1, where do I say the transpose appear here? Where does the transpose come from?
You're asking, where does the transpose come from?
Yeah.
It comes from...
I look at the effective action for the U1 and I don't recognize.
So it comes from how the... So there's spinor indices on these lambdas, right?
Uh-huh.
So it depends on how these are contracted,
Oh, so you
right?
have lambda tilde times lambda, that is a transpose of F slash?
No, lambda tilde, so lambda times lambda tilde is F slash.
Yeah.
But then it depends on how the spinor indices. So this has two spinor indices, right? This has
Mm-hmm.
some alpha and beta. So this has some alpha
Yeah.
beta. And then it depends on how those are contracted.
Mm-hmm.
When I rewrite it
Okay. I
with
see.
those in terms of this trace, I will find that sometimes I get the transpose appearing.
Do you also give the map for the fermionic terms in the action in your paper?
It's so this was already done in the Polycastro Simpis paper.
I see.
So we didn't actually do this in the paper. We just used their result, and we noticed that you have to correct something in the result.
They have given the map.
But it's very easy to see. You mean the map? You mean what lambda times F is, for example?
Yeah.
Yeah, it's very simple to see. So lambda times F will just be the gravitational field strength. I ignored it. Okay, they do it more carefully. There's some overall factor, of course. If you do this very carefully, you have to get the overall factor correct, the normalization here.
But they give it, I see.
Yeah, they do that because they also compute these amplitudes. They also compute the closed string amplitude directally and check that it's the same answer. Okay, so they do it more carefully. So you should look in that paper.
Okay,
But
thank you.
schematically, it will just be the gravitational field strength. Right. So it's easy to write those terms also. But I'm mostly interested in the bosonic terms here. At least, yeah, and it's easier to just write the bosonic terms. If I wrote the fermionic terms, I don't know if I could fit it on a slide, but it's not too complicated. All right, so that's the closed string R to the 4 correction. Now, remember that these same terms appear both at tree level and at one loop. Okay, but because we said the 4-point function is the same, up to the overall coefficient, which I didn't fix here. I didn't put the overall coefficient. At tree level, there's some zeta of 3 alpha prime cubed, and at one loop, there's a zeta 2 alpha prime cubed in front of all of this. But the structure is exactly the same at tree level and one loop. Right, that's what I said. This is theta 3 at tree level and theta 2 at one loop. But beyond the quartic terms, so there are fifth order terms and so on, sixth order up to eighth order, I think. Beyond the quartic terms, they will start to differ. That's obvious because the tree level expression, in the tree level expression, you have r to the 4 multiplied by e to the minus 2 phi, which comes from the string coupling behavior at tree level, whereas there's no such factor at one loop. So if you expand this out, you will see that there's phi times r to the 4 at the 5-point level. So they obviously differ at that level. Right. Now, I also argue that there should be an r to the 4 correction in the M theory effective action in 11 dimensions, and it should be related by the usual dimensional reduction to the type 2a correction. And the type 2a correction you just find here by using the type 2a expression for the Riemann bispinor. So this contains simultaneously both type 2a and type 2b, of course. But how can we find the correction in 11 dimensions so that we can compare it to this correction in 10 dimensions? Well, unlike in the case of the string, we don't have a direct way to compute the M theory effective action. I mean, you should be able to somehow use the BFSS matrix model, but no one's managed to do that to compute the corrections of the effective action. And there's no perturbative expansion in 11 dimensions, so it's not so clear what you should be doing to calculate the M theory effective action. But there's some indirect ways that we can get to it, at least in this case. And one option is, of course, that, if we know that there should be an r to the 4th term, we could just start from the r to the 4 term and supersymmetrize that. And that's expected to give you a unique answer because there's so much supersymmetry, there's 32 supercharges. And this is in principle doable, but and I think people have done this, but the results are quite complicated, so it involves a lot of work. There's another approach which follows more closely the calculation that we did in 10 dimensions, in computing string amplitudes. And the argument is the following. So if you think from a field theory point of view, you start with 11-dimensional supergravity, then you can think of the higher derivative corrections as counter terms, basically. They will appear as counter terms in this non-renormalizable theory. Of course, 11-dimensional supergravity is non-renormalizable. So you will find divergences when you start computing loop corrections. But this will correspond to counter terms which involve these type of high derivative corrections. And they, of course, have to respect the supersymmetry. So in particular, if you compute the one loop 4-point amplitude in 11-dimensional supergravity, it leads to an r to the 4 term with a coefficient which is cutoff dependent. So I think it's cubically divergent, if I remember correctly. And then, but the structure of that, of those terms, if you do it in a way that respects supersymmetry, you will find the supersymmetrization of the R4 term with some divergent coefficient. But you can instead decide to fix that coefficient by comparing to the type 2A string theory result. So this is something that was argued by Russo and Zeitlin, for example, in 97. So this gives you a way, even though the result in... So another way of thinking of it is that you should take a specific cutoff in 11 dimensions so that you find a result that matches with the type 2A result. And this approach was used by Peters, Plefka, and Stern in 2005. And they computed the one-loop 4-point superparticle amplitudes in 11-dimensional supergravity using a certain light cone formalism. So we can use their result and try to compare that to the type 2A correction, keeping in mind that we have to fix the overall coefficient, of course, so that they agree, but we can still compare the structure of the result up to the overall coefficient. So that's what we'll try to do. Now, let me give the result that they found. So they computed, as we said, the 4-point superparticle, one-loop 4-point superparticle amplitudes in 11 dimensions. And they found the following result. There's a T88 R to the 4 term. Okay, remember the hats, all 11-dimensional fields, I put hats on just to distinguish them from the 10-dimensional ones. So as you expect, there's a T88 R to the 4. Okay, that's fine. Then you have various terms that involve 2 Riemann tensors and 2 4-form field strengths. So in 11 dimensions, you have the metric and you have a 3-form field with a 4-form field strength. Okay, and that field strength I called F hat. So those are the only fields in 11 dimensions. So it's a little bit simpler than in 10 dimensions in that sense. We have fewer fields. So you get these R squared, F squared terms. And in the basis that they pick, they take the following form. I think that's 11 terms, if I'm counting correctly. And then you have F to the 4 terms. So the 4th power of this 4-form field strength. And these take the following form. So that's another 10 terms. So that's the result that they found. They tried to write it with as few terms as possible because there's a lot of freedom in making field redefinitions and so on. But this is the way that they presented the result. This was the simplest form that they found. So now we can try to use this result, reduce it to 10 dimensions, and compare it to the result that we found from the string amplitudes. But first, we should remember how we're supposed to relate the 11-dimensional theory to the 10-dimensional one. So let's remember how 11-dimensional supergravity is related to 10-dimensional supergravity. So this is something that's explained in most textbooks. It involves taking a very specific reduction ansatz. So it's not the usual straightforward Kaluza-Klein reduction. It's slightly more complicated. It takes the following form. So the reduction of the metric, the 11-dimensional metric, I've written it here in terms of the field lines. It takes the following form. So the first 10 field lines in 11 dimensions reduced to the 10-dimensional field lines with this factor of the dilaton, e to the minus phi over 3. Whereas the 10th one has a different factor of the dilaton, and it introduces the two-form, sorry, it introduces the one-form Riemann field in 10 dimensions. And we also have the 3-form in 11 dimensions, C3 hat, and the reduction of that, or its field strength, or the F4 hat, reduces to the 4-form field strength of type 2A, together with H, field strength of B, and again, the Riemann 1 form will appear here. So you see that all the fields of type 2A appear here, but in a very funny way. So the dilaton appears in these factors. The 1-form Riemann field comes from the metric, whereas the 3-form comes from the 3-form in 11 dimensions. And the B field also comes from the 3-form in 11 dimensions. So things enter in a kind of funny way. The NS and Riemann sectors are mixed in a funny way here. Okay, they don't appear, the Riemann fields don't appear together as they do in 10 dimensions. Okay, anyway, that's the reduction ansatz. And if you put this ansatz into 11-dimensional supergravity, with a little bit of work, you find that it reduces straightforwardly to type 2A supergravity. Okay, now what we want to do is perform this reduction of the high derivative terms, so the R to the 4 terms. So these are 8 derivative terms. And doing that reduction using this ansatz is a lot more challenging. You see that you will get a bunch of derivatives acting on dilatons everywhere, and it will be kind of a mess if you just try to do that. And actually, that's maybe not so bad. What's even worse is that when you try to relate this then to the 10-dimensional expression, you have to take into account that there's a huge amount of freedom in performing either integrations by parts. We're using Bianchi identities. So, for example, this F4 will satisfy Bianchi identities. The Riemann tensor also has Bianchi identities, right? And you can also do field redefinitions, right? So we have to take into account the fact that we can integrate by parts, we can use Bianchi identities, and we can perform field redefinitions. And there's a huge number of ways you can do that. So that complicates the comparison quite a bit. Now, doing directly...
Can I ask you a very
Yes.
naive question?
Yes.
I mean, isn't somehow the field redefinition fixed by the reduction ansatz that you were using?
No, there are additional field redefinitions that you can do.
Okay.
And that you have to do, actually, it turns out. So we'll see that actually maybe in more detail. I won't spell out exactly the field redefinitions, but we'll see that you need additional field redefinitions. So as I said, if you try to directly just plug this ansatz into these terms, you will get quite a mess. It turns out that you can simplify your work a bit by splitting it up into 3 steps. So equivalently, instead of plugging that ansatz in directly, we can split that ansatz into 3 steps. So in the first step, we perform a Weyl transformation in 11 dimensions, which means we just rescale the metric or the field lines by some factor. Namely, we take e to the 2 phi over 3 and rescale all the field lines by that. So the metric by the square of that. That's the first step. The second step, we perform the reduction by just using a much simpler ansatz, which doesn't involve the dilaton at all. So the first 10 field lines just reduced to the 10-dimensional ones. Okay, I put primes because I've done this Weyl transformation. And then the last one just gives me this Riemann 1 form. And then finally, in the third step, we do another Weyl transformation in 10 dimensions to go to the string frame. And that Weyl transformation looks like this. So we just rescale all the field lines by e to the minus phi. Okay, it turns out that this will simplify things a little bit. Now, of course, the B field and the Riemann one form field strength will arise in the second step when we do this reduction from 10 to 11 dimensions. And they arise in the following way. So if you take the 4-form field strength in 11 dimensions, if one index is in the 10th circle direction, that will give you H, the field strength of B. And similarly, the Riemann tensor in 11 dimensions, for the Weyl rescaled one, which is what the prime denotes, if one index is in the 10th direction, that gives you the derivative of the field strength of the one-form Riemann field in 10 dimensions. So that's how these two fields appear in the reduction. Right, under the Weyl transformation, well, in general, under some Weyl transformation by e to the k phi, because this k was either 2/3 here or -1, so I want to be able to describe them both. So I put this k. So that's step 1 and step 3. The Riemann tensor transforms in the following way, up to higher order terms, which we can forget because we're focused on the 4-point level, so we can drop the higher order terms. The Riemann tensor transforms into the Weyl rescaled field line plus this correction dABCD, which takes this form, so it involves two derivatives of the dilaton and some delta contraction. And for k, where this k is the multiple of the dilaton in the exponent. I can really forget about e to the -2k phi here, because that will just, again, give me higher order terms. Now, it's clear that even the reduction of this r to the 4 term in 11 dimension, just the 4th power of the Riemann tensor, will be very complicated because you have to do these Weyl rescalings, and then when you reduce it, you produce a bunch of additional fields. So you will produce a bunch of dilaton fields and a bunch of Riemann one form fields from this. In fact, it looks a bit strange because you produce a large amount of dilaton terms, but in the way that I wrote the type 2a corrections, there were no dilaton terms at all. All right, I can go back. So I wrote it like this. If you look at this, the dilaton doesn't appear anywhere. This R is just the usual Riemann tensor minus the derivative of H. Right, so it involves the B field and the metric. There's no dilaton term anywhere. Okay, but in this reduction, you produce a huge number of dilaton terms. So it seems that if this is going to work and we're going to reproduce the type 2a result, these dilaton terms must somehow miraculously go away. Right? Of course, we have freedom to do field redefinitions, integration by parts, and so on. So it's possible that it can happen, but there's a large number of terms that have to go away. Now, it turns out that there's a very useful intermediate result that we can derive, because in 2 of the steps, we're doing a Weyl transformation. So if you can simplify what a Weyl transformation does to the r to the 4, so the T8, T8, r to the 4 terms, then it will simplify our work a bit. And it turns out that you can show that up to total derivatives, field redefinitions, and higher order terms, which are not relevant for us, a Weyl transformation by e to the k phi transforms the T8, T8, r to the 4 terms in the following way. So it produces the T8, T8, r to the 4 of the Weyl rescaled metric plus the following correction. Okay. Again, I'm dropping any higher order terms. So these are just the Bordic terms. But I'm doing this in the general dimension. So k is the exponent here that appears. D is the dimension. And L is given by the linearized equation of motion. So if the linearized equation of motion is RAB is L times the second derivative of the dilaton, that L is what appears in here. Okay. Then I have this factor of 2 derivatives of the dilaton, 2 of those factors times this x, where this x combination is some r squared terms plus some phi squared terms, basically. It takes more precisely, it takes this 4. But the exact form is not super important. The important point here is that I've managed to, so if I just did the wide rescaling, I would find terms that are linear in the dilettante, quadratic, cubic, and so on. But here I've managed to simplify it so that there are only even powers of the dilettante appearing, because there's phi squared here, and this x either is r squared or phi squared. So you get r4, phi squared, r squared, and phi to the 4 terms. Okay, so that's a bit of a simplification, but the dilettante terms don't go away completely. But with this intermediate result, we can now carry out the reduction of the T8 term, T8 R4 term in 11 dimensions. So let's go through the steps. So the first step is to do a Wulff transformation in 11 dimensions. And that turns out, so we want to take k equals 2/3, and it turns out that L is 0 there. And if you plug that in to this expression, you will find that Wulff transformation does the following. You get the Wulff transformed T8, then you get this, but this x is just this, but in 11 dimensions. Then we do the reduction, which is step 2. When you do that, you will generate some other terms. So you find this will reduce to the T8 R4, of course, but it will also give you R squared F2 squared terms and F2 the 4 terms, okay? Because this gives you the derivative of the Riemann 1 form, or the field strength of the Riemann 1 form. Also, when you do the reduction, because of this, okay? If one index is in the empty circle direction. Okay, so that reduces those terms, and then we have this still. We have to reduce that. It gives you another, it gives you just a straightforward reduction, which is this in 10 dimensions. But then again, all these indices are in 11 dimensions, so they can give rise to F2 terms. And those are in the X tilde, so these are quadratic in the field strength of the Riemann 1 form. Well, it looks like this, but the precise details are not important. The important thing is that it's some F squared term. So this is phi squared F squared, basically. Right, so that's the reduction step. And then, so these terms, the R squared F squared terms, if you write them out explicitly, they take this form. I have to shrink it just to fit it on the page. So it's just somewhat complicated, but they have some form. They're of the form R squared, F2 squared. And the final step is to perform the last Weyl rescaling in 10 dimensions to go to the string frame. That means taking, in our expression, k is -1 and L is -6. And then it turns out that if you do that, these x terms, remember this x was this funny expression. It's present here. Now you'll generate another one from the Weyl rescaling of this guy. And it turns out that the two cancel, actually, in a slightly miraculous way. So that's quite nice. But you're still left with the following terms. So you have the T8 R4, of course, just the Weyl rescaling of this. Then these terms are still there. We have those terms still there. And then we have that term, which moves this, is still there. So this is phi squared F squared terms. And you notice here that I still wrote this R prime here. So it's actually not just the Riemann tensor, it's the Riemann tensor shifted by this dilettante term. So there's also dilettante terms here, right? Now, if we try to compare this, so now we've done all the steps to reduce the R to the 4 term from 11 to 10 dimensions. And now we should compare this expression to what we have in type 2a. Now, if you look at the first term, it's precisely what we expect, right? It's T8 R to the 4th. That's the term that we have in type 2a. So that's good. But if you look at the second and the fourth term here, they're quadratic in F2. This is also quadratic in F2. So they should be compared to the terms that are quadratic in the Riemann field strength F2. So that's sitting in the Riemann bispinner in the type 2A result. So this should be compared to the corresponding term that's quadratic in the Riemann bispinner. So that's the following. Well, I wrote two terms, but I can combine them into this one term. So this is the type 2A result, which should be compared. So you should extract the F2 terms from this Riemann bispinner and compare it to the F2 terms from here and from here. Okay. And then, of course, the F4 terms, I didn't write them out, but let's focus on the F2 terms quadratic in F2. Now, it looks that this could not possibly work because, as we said, from the reduction, we get terms that are linear and quadratic in the dilatons. We get phi r F2 squared and phi square F2 squared terms. And it turns out that these terms don't cancel out. You can't get rid of them by field redefinition. But on the type 2A side, as we said, there are no terms involving the dilaton. So what's going on here? So this has dilaton terms, this has dilaton terms. But the type 2A result doesn't have any dilaton terms. But if you're a little bit more careful, you notice that when you evaluate the gamma traces here, so we have a trace, this Riemann bispinner, and a bunch of gamma matrices. When you evaluate these traces, it can happen that, say, this gamma G could become contracted with gamma E. And in this term, that will produce a contraction of E and G. So that will produce a term involving the Ricci tensor. So actually, when you carry out the traces over the gamma matrices, you can produce Ricci tensor terms. But those can actually be replaced by terms involving the dilaton by field redefinition, because the lowest order equation of motion, the linearized equation of motion, looks like this. So it's the Ricci tensor is twice second derivative of the dilaton. That's the linearized equation of motion, which is all that's relevant here, because we're neglecting all higher order terms. So that means that by field redefinition, you can replace the Ricci terms by derivatives of the dilaton. So in that way, you will generate dilaton terms here in the type 2A result. So that can potentially resolve this tension. And in fact, this will introduce clearly terms that are linear or quadratic in the dilaton, because you can have either one or both of these R's converted into a Ricci tensor by those contractions. And in fact, if you work it out, it's a bit of work, but you find that the two expressions match precisely, again, after field redefinitions and integrations by parts and dropping higher order terms, right? So although they looked very different, these expressions, it turns out that they actually match on the nose. Now, this was just the R to the 4 term, right? The T8, T8, R4 term in 11 dimensions. We can continue and do the reduction of the R square, F square terms, F4 square terms in 11 dimensions. There were 11 of those in the result that Peters, Plefka, and Stern wrote. And we can also do the 10 terms that have the 4th power of the 4-form field strength squared, right? Remember, these are these expressions here. So these terms and these terms. Let's see. And if we do the R square, F square, F4 square terms, it produces quite a lot of different terms. It produces all these terms schematically in 10 dimensions. So terms of the structure R square, H square. Again, to make this more readable, I put the NS sector terms in blue and the Riemann terms in pink. Okay, so you get R square, H square, R square, F4 square, RH, F2, F4, blah, blah, blah. Also dilaton terms, phi square, F4 squared, a bunch of different terms. But again, with a bit of work, you can show that this reproduces precisely the terms that you get in type 2A. Except that it doesn't quite work. You have to rescale the result of Peters, Plefka, and Stern by a factor of 6 for it to work. There's an overall coefficient which doesn't match. And actually, it seems that that's the mistake in their paper. They missed the symmetrization factors that you have in relating the amplitudes to terms in the Lagrangian. So I think that's the origin of this missing factor of 6 in the paper. Okay, but fixing that factor of 6, everything again matches, but in a very non-trivial way. And then finally, the F4 terms in 11 dimensions, these are a bit easier to reduce. And again, you can show that they match the F4 terms that you extract from the terms quartic in the Riemann spinner in the type 2A case. Okay, so in that way, we have completed the proof that the 11-dimensional R4 terms that are computed from the one-loop 4-point superparticle amplitudes reduce precisely to the corresponding terms in the type 2A one-loop calculation. Of course, this is after we fix the overall factor. The overall factor we cannot fix in an independent way in 11 dimensions. But the structure of the terms is precisely correct. And this is consistent with the expectation that we have that probably both of these corrections, both in 10 and 11 dimensions, the correction is uniquely fixed by the maximal supersymmetry. There's no proof of that as far as I know, but it's a reasonable thing to expect given the very large amount of supersymmetry. In fact, maximal amount of supersymmetry. Okay, so now there's just one more thing. So we managed to match the 11-dimensional and the 10-dimensional expression, but the 11-dimensional expression that we started with, the one that was computed from superparticle amplitudes, didn't have a very simple or natural form. Particularly the R to the 4 term was what we expect, T8, T8, R4, but we have these 11 R squared F4 squared terms and 10 F4 squared terms, so over 20 terms that did not have a particularly nice structure, whereas the 10-dimensional expression was much more compact, right? So maybe I'll go back to these expressions. So the 11-dimensional expression was this. So this is the R squared, F squared terms, and these are the F4 terms. Now, if you compare that to the 10-dimensional expression, that's this. So this is just 6 terms. So 2 R squared, F squared terms and 3 F to the 4 terms. Of course, you generate a bunch of terms if you expand out these gamma traces, but this is quite a compact way of writing it compared to this. Right? So we expect that in 11 dimensions, it should be possible to write something more compact, more similar to the type 2A expression. And actually, with some work, you can show, again, using integration by parts, Bianchi identities, and fielder definitions, if we now define an F slash in 11 dimensions, which is just the 4-form field strength contracted with 4 gamma matrices, then, so these are now 11 dimensional, so 32 by 32 gamma matrices. If we define that, we can show that you can write this rather complicated expression with more than 20 terms in this compact form. So we have the R4 term, the R squared terms combine into this expression, which is basically, it looks exactly the same as the 10-dimensional expression, except for a factor of 2 and the fact that the gamma matrices are 32 by 32 instead of 16 by 16. And then we have these 3 F to the 4 terms. Okay, so this shows that you can find a much simpler expression or a much more compact expression, at least in 11 dimensions. Of course, if you want it written out explicitly, then evaluating these gamma traces will produce a bunch of terms again. But this is a compact way of writing the expression. And more than that, it makes it very easy to show that some of the terms correctly reduce to the 10-dimensional one. So the F4 terms, you can see directly from here. So the F4, the terms that involve the 4-form Riemann field, you can see directly that the reduction produces the correct terms in 10 dimensions from this expression. Okay, so I'm out of time, so let me end with some conclusions and outlook. So we have seen that the 4-point R to the 4 correction in 11 dimensions, indeed, as expected, reduces to the type 2A R to the 4 corrections, R to the 4 correction. Okay, but we checked this for all the terms. Previously, this was only checked for the metric and I think B field terms, but certainly not Riemann terms and all dilaton terms and so on. And we've seen that it does reduce correctly, but it does so in a very non-trivial way. You generate a bunch of dilaton terms that you then have to get rid of. There are lots of field redefinitions and so on that you have to do in the process. And then we've used the compact form of the R to the 4 terms in 10 dimensions to find a similar compact form for the quartic terms in 11 dimensions, which is this expression. Now, what's the next step? Well, the natural next step is, of course, to go beyond the quartic level. So the next would be the 5th order in fields. At this order, as we said, the tree level and the one-loop correction will start to differ. So things will become more complicated and also more interesting. Furthermore, we only have partial knowledge of these terms. So scattered in the literature, there are some subset of these terms are known. In the NSNS sector, I think we know all the terms, but in the Riemann sector, we have only partial information. And computing amplitudes becomes more complicated, but probably supersymmetry or possibly using dualities like SL2R for type 2b could be a way forward to fix these terms once we know the quartic terms. All right, that's it. I will stop there. Thank you for your attention.
Thanks for the very nice talk.
Thank you.
Hi, Linus. Thanks for the nice talk.
Hi.
Can you hear me?
Yes.
Yeah, Parita here, by the way. I'm sorry, my laptop just died midway, so had to come through a different mode. Yeah, I have a nice question, perhaps. What can you say about Horova-Witten type theories to connect with heterotic cases where, like, let's say if you want to consider much lower order corrections, like what happens there?
Oh, for the heterotic. So I focus on the type 2 theories and the case of maximal supersymmetry.
Yeah.
If you can ask similar questions for the heterotic string. There's a bit more complicated. So one of the reasons for focusing on type 2 is that you have the largest amount of supersymmetry, so the corrections are the most constrained. And in particular, that means that the first correction here in this expansion starts at alpha prime cubed. Whereas for the heterotic string, it turns out that there's a correction already at order alpha prime. In fact, this is connected to the Green-Schwarz anomaly cancellation mechanism. So the corrections start already at order alpha prime. So then you have to start, well, I mean, at least if you want to start from the lowest correction, which you normally want to do, you should start at order alpha prime. And that generates an alpha prime square correction. But there is also the same alpha prime cube T8, T8, R4 correction in the heterotic case. So you can try to, and again, this will have a coefficient state of 3, which the lower corrections will not have. So you can try to talk about just that correction. But yeah, it depends what you want to do. You can try to isolate that correction, but then you're ignoring the fact that you have more leading corrections at order alpha prime and alpha prime squared, which maybe you want to take care of first. But you could try to relate that to via the Horova-Witten story to the 11-dimensional case, which is what you're asking. And that I don't know whether anyone has tried to do that, actually. It's an interesting question. It should be possible.
Thank you.
Linus, can you comment more how much of the techniques that you use for the 4-point case you can use at the higher one?
Which technique specific? You mean that amplitude
Well,
story?
Yeah, at the level of the amplitudes, but also the fact that essentially you constructed I mean, you kind of use the double copy in some sense, right? You were reconstructing the result by taking the open string 1 etc.
Yeah.
How much is going to go through, and also the field definitions, you might not be able to use them anymore because, yeah.
Well, so yeah, it will certainly be much more complicated. So let's say I want to go include the 5-point terms. So trying to follow the same approach would mean I want to compute now the 5-point function as well. Now, as you said, I can't directly use the double copy if because I can use it at the leading order and linearized level, but if I want to include the subleading corrections at 5-point, I can't directly do that. Of course, I can try to directly compute the 5-point amplitude in string theory. The problem is that, well, now I can compute it at tree level or one loop, but if I want to relate to 11 dimensions, the correction that's straightforwardly related to 11 dimensions is the one loop correction in type 2a. So then I should compute a one loop 5-point function. Okay, that involves some work. I believe it's possible to do, but then to write the result in some reasonable form, it certainly hasn't been done. So there's a lot of complication there. And then, of course, as you said, with all the field redefinitions, what I did at the 4-point level is, I drop all the higher order terms that I generate. Now I have to go back and do it again and keep all those higher order terms, at least the 5th order terms. That means that I generate, when doing the 4-point calculation, we're redoing that. I generate a bunch of 5th order terms, and then I have additional terms coming from the 5-point function. And then I should relate that. So I should do a 5-point one loop computation in 11 dimensions and in 10 dimensions and relate those. Keeping in mind all the extra terms that I generated that I neglected now. Okay, so that's quite a tall order, I think. Probably a better starting point is to just start from the R4 terms and supersymmetrizing them and keeping the subleading terms. Or for, say, type 2b, if I'm interested in a type 2b effective, the type 2b correction, I can use the SL to R or SL to C duality symmetry and try to kind of bootstrap the result starting from the leading terms. I think those are the more promising ways of doing it rather than, because if I wanted to compute the full correction, which will contain up to 8th order in fields, I would have to compute an 8-point one loop amplitude, which is, it's not going to happen anytime soon. Whereas there is some chance that using supersymmetry or duality symmetries or both, at least you have a better chance of nailing down the higher order terms in that way, I think. So I don't know if that answers your question.
Yeah, thanks.
Okay, thanks.
How about superspace in 11D supergravity? And
Yeah.
if we know that, maybe you can supersymmetrize the term in one loop.
Yeah, so the calculation they did, so Peters, Plefka, and Stern, the calculation they did is using some light cone formalism, but it is supersymmetric, right? So that's the point of their calculation, right? So if you use some component formalism and try to calculate all these one loop terms in 11-dimensional supergravity, I think it's very complicated. But this light cone approach is relatively powerful. But in principle, you could use some other superspace approach, but I don't think it's been done. I don't know really what's available in 11 dimensions. It seems that the light cone approach is relatively powerful, but I don't know actually for higher point. I think it becomes more complicated for higher point. I think there's some special simplifications that occur at the 4-point level. I believe they have some comment about this, but
yeah, 5-point, you will have epsilon 10 times epsilon 10 to the 4 as well.
Yeah. That would, of course, be nice to nail down those terms as well. I think
those terms has been
there may be some partial results there.
Yeah.
There are also partial results from trying to directly supersymmetrize R to the 4 in 11 dimensions. There's this Japanese guy who's been doing this for a long time.
Yes.
But again, I think they're only partial results, and I think again they're written in quite a complicated way.
Mhm.
Another approach would be to try to take those partial results and write them in a simpler way. If you have some hints for what sort of structure you should aim for, that may also be a way forward. But I think still the comparison to the 10-dimensional result for the higher point terms is going to be very complicated because of all the field redefinitions that you need.
Yeah. Does the amplitude for ABGM have a double copy interpretation which can shed lights for 11D supergravity? And this in
Good
ADS.
question. I don't know is the short answer. I don't know. What would that?
But I mean,
What would
are
that-
you guaranteed that it's going to work? This is what I think. I mean, you can do that, but is there a proof that it needs to give you the correct answer?
There is a by computing like 5-point function for energy momentum tensor, which will translate into 5-point function for graviton in the ADS background. Yeah, I think Shein has done some work 10 years ago and the level. They didn't look at the 5-point function for the energy momentum tensor in ABGM theory. Yeah. And 4-point
it's
function.
It's
Yeah.
an interesting question. I don't know actually what you can learn from ABGM, but yeah, there is some story. No, there is some story with with using ABGM to find high derivative corrections or compared to high derivative corrections in 11 dimensions. That's true. I don't know if it uses double copy in some way. But yeah, there are certainly other approaches to try to find the high derivative corrections, r to the 4 or higher. There are also terms with derivatives. So whatever it is, d to the 8, r to the 4, something at higher orders.
Yeah, I think they use holography, just compute higher point.
Yeah. Yeah, so yeah, that's a good point. So holography is one way that you can try to get to the corrections to the M theory effective action. So I said we have no direct way of calculating it, but yeah, of course, holography is another indirect way that you can try to get to these high derivative corrections. Typically, when people do this, they tend to just look at the metric, but I don't see why. I mean, you should be able to do it in a supersymmetric way and get the full correction in principle.
Yeah, in the ABGM side, I don't know how difficult to compute like 5-point function for T mu nu, and then because supersymmetry, you can know other high point functions for the with the T mu nu. Because in 3D, the tensor structure is not too bad, I guess. Tensor structure.
Yeah.
Because you can have some spinner formulation for that.
Yeah, I think the results that I've seen are still at the 4-point level, but also including some higher order corrections which involve additional derivatives. But typically they're just at the 4-point level. But
in principle, one
you
should
should be able to
compute the
go
5-point.
But yeah, I don't know what that would involve actually.
Yeah,
it from
nobody has done that.
No, I don't think so. As far as I know, anyway.
And T mu, you don't have to worry about field definition, so on, I guess.
Yeah, I mean the field definitions are always a bit of a hassle, and well, it's more than that. I mean, Bianchi identities and integration by parts means that you can write things in a lot of different ways.
Yeah, I think I have asked all my questions.
Okay, then we can probably thanks again, Linus.
Thank you.